This video will explain how to make a size in Zeta potential measurement on the Nicomp DLS system using the Nicomp Net software. To begin with, let's measure the 90 nanometer polystyrene latex standard that is supplied with the system.
First, we'll prepare a 10 millimolar sodium chloride or potassium chloride solution. We'll filter this to remove any particles. We'll then take 30 microliters of the standard and dilute that into 5 ml of the filtered salt solution. Take measurements that are 5 or 10 minutes long and check the result to the standard. The graph you see here shows the difference between measuring this sample in DI water as opposed to a salt solution, and you'll see sometimes you can get away with it. More often you're better off doing it in the salt solution. This graph is part of a larger technical note, which you see here, which will explain all the details of how to take these measurements using the size standard.
Here I'm going to use the round glass cells in the black cell holder. I place the tube into the black cell holder. I'm going to pipette the standard into the cell so that it is above that cutout where the measurement is made. Then I can take this cell and load it into the instrument for measurement. This is the proper orientation for loading the size cell. The cutout where the measurement is made is oriented to the right, and the solid side is oriented to the left as you face the front of the instrument. Load the cell oriented as just described. There's a black plate in here. You move over to the left and make sure that this is in the position for size, not Zeta, if it's a Zeta system, and then close the door. It's a good idea when we get started to create a new database. We click here, Create New Database. I'll call this Installation. And I'll put the data there that I collect during the installation. There, we've created that. Before we make a measurement, first we want to create a measurement protocol. So we click here on Protocol, and this will open this dialog box. I'll call this protocol PSL, that's short for polystyrene latex standard. Sometimes on the description, maybe I'd put in the lot number of the standard I'm using. If I want to print a report at the completion of the measurement automatically, I could come in here and say, please print the intensity weighted Gaussian, for instance. I'm going to use the round glass cell, so I'll choose the cell. We typically make all of our measurements at 23C, and we see down here under viscosity, that is the viscosity of water at 23C. If we ever do make a measurement in a liquid that has a higher viscosity, we'll want to alter this value because any error in viscosity will create a proportional error in the reported particle size. I'm going to make, this is set to make 1. Typically we would make 3 measurements of the standard and then take the average. I'm working with a system that's collecting data at 90 degrees. This is the equilibration time. Give it time to reach the desired temperature. A Peltier is bringing the temperature to the set point of 23C. The sample volume here really doesn't matter. The sample is defined by what is inside the cell. I'm going to manually stop the measurement after 5 minutes. The official procedure for the latex standard is 10 minutes. And here are various settings for both how we take the measurement and how we can make certain calculations. But if we're new to the system, we'll just leave all of these selections to automatic, and then the system will automatically choose the settings that it deems appropriate based on what it sees from the light scattering. We would only change this option to vesicle if we were measuring liposomes. We leave that on solid particle for everything else. And on this screen, I actually have to maximize this to get down to here where I can save the protocol. And now we have saved that protocol. Okay, after creating the protocol, now we're going to run the size standard. And you might think, well, I just click run, but what you're going to see is it's saying, oops, we first have to initialize the neutral density filter. This is an optical filter that varies the intensity of the light source coming into the sample, and this is how we control the count rate. And the reason we got that error is because the first run of the day we need to come into configure, And under maintenance, we need to click here on Initialize Neutral Density Filter. And if you are listening to the instrument, you can hear that's a wheel turning. And it's going to adjust this neutral density filter and understand the relationship between setting and count rate. So we're just going to give that some time. It looks like this has now been set. We can click OK. And now when we come up and click Run, we can say that this is a sample name, 90 nanometer PSL 1 maybe. The lot number, I guess, maybe this is where I should enter the lot number. We're going to do a manual measurement, meaning stop after 5 minutes. And under project, we haven't created a project yet, so we're going to create the project installation. And that is where it will store this data. We can now click Run, and now we'll look at the process that occurs when we begin measurements. And I'll need to fast forward through some of this. First, it's adjusting that neutral density filter again to optimize the count rate, typically to be in the range of 300 kilohertz. We can see that on the screen on the front of the Nicomp. We will also get a readout of that when we start measuring. The system is now adjusting the channel width. This is one of the settings we told it to do automatically in the protocol. Up here is where we're seeing the count rate. It's available here as well as on the front of the system. There are some other internal settings being adjusted now. Now we're going to start collecting data. You see this running showing up down here. There's a delay, and now we start seeing the results. Now the first result you see is not the perfect result. We want to collect data for a while before we start generating very accurate results. Although for 90 nanometer standard, you see we're at 89.5, so that's not so bad. So what we see in the upper left is the current intensity mean diameter. And be patient, we want to collect the data for a while for this number to be optimized. The correlation function you see here is the raw data. And what we do is look at this curve and from that do a certain fitting to come up with the diffusion coefficient, which we then use to calculate the particle size. On the right-hand side, we see history. And here we're looking at the mean diameter based on intensity, volume, and number. The important value is the red number here, and we want that number to be stabilized. Over here on the right, we see we're looking at the intensity distribution, but we could switch that to volume or to number here. The Gaussian is how we always run standards. A Gaussian forces the result into a single peak, and this is a single peak latex, so we would always leave that at Gaussian. We'd click on Nicomp when we try to split this into 2 or more modes. We currently have the display in bars as opposed to a line chart. I like the bars for a single run and the line chart to compare multiple runs. We see how much time we are into this measurement. We'd like to see typically on the order of magnitude of about 2.5 decays. That is about how we fit to this curve. We are collecting data at 90 degrees here. Chi-square is a calculation to tell us how good is the fit to a Gaussian distribution. If that number gets up over 4 or so, maybe we would consider the Nicomp distribution. The baseline adjust is telling us, are we seeing stray noise, maybe, coming from some large particles? Are we having to adjust for that? Seeing 0 for the baseline adjust means we have a very clean sample. We have our fit error, that looks under control. Down here we just have the run name and the information we had input at the start of the measurement. So now we see that this red line, all the numbers have pretty well stabilized after about 2.5 minutes. But that's because this is a very narrow, easy distribution. We should never be in a hurry running dynamic light scattering. Take your time. And the broader the distribution, the more width to the distribution, or the more complex the distribution, the longer you want to analyze to get the best results. This happens to be about the easiest sample you can run, so this will stabilize fairly quickly. So this is now going to run for another 2 minutes before we get our final result. I'll stop here and we'll fast forward to the final measurement. And there we are. We now have completed our first measurement. And we see the result here of 91.92 nanometers. I would need to look at the certificate of analysis. I think this is a 92 or 93 nanometer standard. So that looks very good. The polydispersity index is very low, so this was a very successful first run of our size standard. I completed 3 measurements of the latex standard. Now let's look at some of these results. I'm going to just move this up here just to get a better view of the data down here. Under database, I have chosen to look at the database installation. This is the third of the 3 results. By clicking in these boxes, I can add any of the other results to the same plot. Look at one or multiple plots. So here is result number 1, result 2, result 3. You'll see we have essentially the exact same mean diameter with some change in the width or breadth of the distribution, but I'm not worried about that. Our specifications are on the intensity mean. So these look like 3 successful runs of the standard. One of the things I could do now, if I have the rights to approve or reject results, I could say this result number 1, I can click on approve, enter a username and a password. There we go. I can now sign, and that result has now been approved. This video will now move on to how to make the zeta potential measurements for instruments that are configured for size plus zeta potential. To provide a little background on zeta potential, this is the charge on the surface of the particle. So if this particle is negatively charged, it will move towards the positive pole. We place the sample in this cell. We apply an electric field, and the direction the particle moves in tells us was the particle positively or negatively charged. We also measure the speed the particle works at, and that tells us the magnitude of the charge. Was it 10 millivolts or 40 millivolts? During the installation, we're going to mix up a standard. This is the ZRS standard. We do that by placing 0.05 grams into 100 ml of water. We'll mix it for 3 minutes, measure it while applying 4 volts per centimeter in the applied electric field. We'll measure it 3 times for 5 minutes, and then we will compare the result we achieved, the average result, to the value we see here on the certificate of analysis. So we match up our final average result to the value we see here on the certificate that comes with the ZRS standard. So I bring a weigh dish over to a balance, and then I'm going to tare the weigh dish, add 0.05 grams of the ZRS powder, and it doesn't have to be super accurate. You'll see here I end up adding 0.055, and that will be good enough. And then I take that powder and dump that into a beaker with 100 ml of DI water, and we'll mix it for 3 minutes. Take one of the square plastic disposable cells, fill it about 3/4 full of the mixed ZRS standard. Then insert the electrodes. And it doesn't matter if there's a small amount of air at the very top. That should be okay. Orient it so the word plastic is facing the front. Attach the electrodes to the cell and place it into the system for measurement.
Here is a top view of loading the zeta potential cell. Connect the electrodes, put it down into the cell holder. Move this metal plate over to the left. Make sure that this slider is to the right, saying zeta. Close the door.
Okay, now let's switch over and make a measurement of zeta potential. If we choose Run, we come here to Measurement Type and change this to Zeta. I created a protocol earlier called ZRS. We could create a protocol by clicking here. And here we would choose options such as, we keep the temperature fixed, we keep these angles fixed. Really, the only value I changed for this particular protocol was when we measure the ZRS standard, we measure it using an electric field strength of 4 volts per centimeter. We keep everything else here. Typically, I will stop after 5 measurements. And if I were really measuring the standard, I would make 3 measurements and do an average. I need to just make this larger to be able to get down to the save protocol. I will call this protocol ZRS X3, 3 measurements. I could save that protocol. That is saved. Okay. So now when we come up here to choose a protocol, we can choose a protocol. And I'm going to say ZRS1, something like that. And we could then run this protocol, but there's another step we want to perform before we do that. Before we make our first zeta potential measurement, one thing we want to do is check the intensity of the zeta reference beam. To do this, we click on Configure. And over here, I want to click on Zeta reference beam, turn that on, click Apply, and then OK. And then on the front of the Nicomp system, there's a display showing the intensity, and we want to see that above 2 megahertz. So we just check to make sure that we have that intensity, and then we can turn it off again by going to Configure, turn off the Zeta reference beam, Apply, OK. And that should now drop down to the usual level we see for measurements of about 300, 600 kilohertz. And we just want to do this once. What we're doing is we're checking to make sure that the laser beams are aligned properly for making zeta potential measurements. To make a zeta potential measurement, we're going to come up to Run. Here we're going to choose Manual Zeta Potential Measurement. We choose the protocol. I will choose ZRS. We enter a name. This is ZRS install, something like that. And we want to measure the Zeta Potential Reference Standard, the ZRS, during the installation. We now click Run, and that's pretty much what there is to it. There's going to be some initialization steps. It's going to check the Zeta reference beam. I've shown previously how to make sure that that is a high enough intensity and that the laser has been aligned properly. It will then go through and make sure we have the light scattering at the level we want and a few other internal adjustments. We see the flashing red down here running, so it's in the process of preparing to take the measurement. After it checks some reference data, we now see the first indication of a result up here, which is minus 47 millivolts. So we give this some time. I think I set this up to do a 5-minute measurement. And what we're going to do is choose the value at the end of the measurement. That value at the end is the average over the period of the measurement duration. In the two boxes up here, we see the phase shift and we see the cell current. That gives us some indication if something went wrong, but everything looks appropriate here. This is the current passing through the cell in the applied electric field. So now we'll wait until we complete the measurement, and that will be a few minutes, so we will fast forward to that. At the end of a measurement, this is what the result looks like, and we would use this value, minus 47.58, as the average zeta potential over the course of this measurement. We would compare this to the value on the certificate of analysis that comes with the ZRS standard. If we want to view stored zeta potential measurements, we can come to the Sample Explorer. I'm just going to pull this up so I can have a better view. And under this project installation on this date, I can see I made multiple zeta potential measurements, and I could view results here. I would need to adjust my screen again to be able to see those. Perhaps if we were using a different resolution setting on screens, that would be easier to see. But down here is where we can view zeta potential results and also go through this business of approving or not approving a result. So I could click here to a result, and then I could click approve or reject that result. The palladium electrodes that were supplied with the system should last many years, but some samples may burn and/or discolor the electrodes. So when they turn black, you want to take the file that was provided with the original shipment and file the electrodes until they become shiny and silver again. This is a nice new clean set of electrodes. See how they're very silver? When they turn black, you need to clean them with the file that's provided. When those turn black, you just file it down, remove the black color until it turns silver and shiny again. During the installation, we're going to measure the 90 nanometer polystyrene latex size standard that is supplied with the instrument. Before we make a measurement, first we want to create a measurement protocol. So we click here on protocol, and this will open this dialog box. I'll call this protocol PSL, that's short for polystyrene latex standard. Sometimes on the description, maybe I'd put in the lot number of the standard I'm using. If I want to print a report at the completion of the measurement automatically, I could come in here and say, please print the intensity weighted Gaussian, for instance. I'm going to use the round glass cell, so I'll choose the cell. We typically make all of our measurements at 23C, and we see down here under viscosity, that is the viscosity of water at 23C. If we ever do make a measurement in a liquid that has a higher viscosity, we'll want to alter this value because any error in viscosity will create a proportional error in the reported particle size. I'm going to make, this is set to make one. Typically we would make 3 measurements of the standard and then take the average. I'm working with a system that's collecting data at 90 degrees. This is the equilibration time. Give it time to reach the desired temperature. A Peltier is bringing the temperature to the set point of 23C. The sample volume here really doesn't matter. The sample is defined by what is inside the cell. I'm going to manually stop the measurement after 5 minutes. The official procedure for the latex standard is 10 minutes. And here are various settings for both how we take the measurement and how we can make certain calculations. But if we're new to the system, we'll just leave all of these selections to automatic. And then the system will automatically choose the settings that it deems appropriate based on what it sees from the light scattering. We would only change this option to vesicle if we were measuring liposomes. We leave that on solid particle for everything else. And on this screen, I actually have to maximize this to get down to here where I can save the protocol. And now we have saved that protocol.